In the last class, we looked at definitions of trees. We saw what a tree was, what a binary tree is, what's a complete binary tree, what the height of these things are. Today, we are going to continue with our discussion on trees. In particular, we are going to talk of what are called tree walks or tree traversals. So, a tree walk is a way of visiting the nodes of a tree in a specified order. And there are two different tree walks that we will first consider. One is called a pre-order walk, the other is called a post-order walk. So, in a pre-order walk, what happens is that you first visit or process each node and then you go and process its children. Okay. I will show you soon examples of all of this, so that this is clearer. In a post-order, you will first process all the children or visit all the children, and only after you have done that would you process the node. Okay. So, let us see examples which will clarify this thing. Some problem with my So, I am looking at examples of pre-order tree walks here. So, suppose you have, so recall that we said that a book or a paper, we can construct a tree out of it, right. We can look at the organization of a book as a tree. So, or let us say a research paper. So, you have the paper, it has certain sections. So, the first section, let us say, is the title. The second section is the abstract, which discusses what is there in the paper, and then you have section 1, section 2, section 3, and then at the end of it you have references as to what are the books or the other papers that this particular publication has referenced. Section 1, let us say, has two subsections, section 1.1 and 1.2, section 2 has 3 subsections, section 3 has 2 subsections, and so on and on, right. Now, when you start reading the paper, when you read the paper, this is the order you would go in, right. Suppose you are reading the paper end to end. So, first you will go to the title, then you will read the abstract, then you will look at, start with section 1, subsection 1.1 in there, then 1.2, and so on and on, right. If you were to think of the listing as the table of contents, if you were to think of a book and how the table of contents of the book are listed, right. So, the way the table of contents are listed is that first you have the chapter, and then are listed the sections within the chapter, and then the next chapter, and then the subsections within the chapter, and so on, right. So, if I were to look at this as a tree and these as the nodes of the tree, then the first node that we are referring to or accessing is this node 1, right. Then we go to this node 2, then we go to 3, then we go to 4, then 5, then 6, and after we are done with 6, in a table of contents you will have this 7 and 8, 9, 10, then 11, 12, 13, then 14. Yeah. So, this is also called the pre-order traversal of a tree, right. And pseudocode for pre-order traversal would look something like this. So, if I have to do the pre-order traversal of a node V in the tree, so to begin with, I would call pre-order traversal at the root of the tree. Then I would say first visit the node. So, visit here is a generic term, we will use visit very often. All it means is that I am doing some computation at that node. In this particular case, if I were listing out the book as the table of contents, then visit would correspond to print the title, print the heading, or print the title of that particular node, right. So, for instance, each node corresponds to a section or some such thing, then this would correspond to saying print out the name of the section, right. And then once you have done that, then you go to each of the children nodes and repeat the process there, repeat this same process there on each of the child nodes, right, because this tree could be arbitrarily deep. Right. I could, this section subsection 1.1 could be in 3 subsections, 1.1.1, 1.1.2, and so on and on, right. So, if you were to do a pre-order traversal, then you would come to 1, then you would come to 1.1, then you would go to 1.1.1, 1.1.2, 1.1.3, and only then would you go to 1.2. Right. So, that is the need for this kind of a recursive traversal. So, what you are doing here, you will first visit the node, then visit all its children. So, these are the 6 children of that node. So, we are saying visit this. So, what does visit here correspond to? Well, it does not have any children. So, it just means visit this node. This corresponds to visit this node. This corresponds to visit this node and then visits its children. So, that is what we are doing, visit its children and then the next child, yeah, and so on and on. So, this is what would be called a pre-order traversal. Yeah. This is different from, so this is the, I gave you the example, it is like reading a document from beginning to end. Yeah. Now, we could also have what is called a post order traversal. Now, in a post order traversal, recall I said what we are going to do is we are going to visit the node at the end. We will first visit its children and only then we would visit the node. Okay. So, let us say I have a directory structure like this. Okay. So, this is my, let us say, root directory courses. In that there are two. So, this is an example from the book. There is 2 courses, CS016 and CS252, and then in there are 2 subdirectories. There is a file called grades. Within this subdirectory there are 3 files. Within this subdirectory there are 3 files, and so on and on. This is the directory structure. Okay. Now, suppose I want to compute the total space occupied by this file system, let us say this entire directory. Okay. Now, what would I do? Well, I would compute the total space occupied by this subdirectory, I would compute the total space occupied by this subdirectory, and then I would add these 2 up at this node to obtain the total space required here. Yes. So, in some sense the computation that I am doing, I am actually visiting this node or doing some computation on this node after having done the computation at the 2 children nodes. After having computed the total space required by this subdirectory and after having computed the total space required by this subdirectory, only then am I doing this, right. So, in a post order traversal, what you do is that for every child of the node, when you are doing a post order traversal of a node V, for every child of the node you are first going to perform a post order on that. So, in this example, post order here corresponds to finding the total space occupied by that subdirectory. So, to compute the total space occupied by this directory, you are first going to compute the total space occupied by this subdirectory, the total space occupied by this subdirectory, and having computed that, you are then going to compute the total space required by this directory. So, in some sense the order in which the computation is done is reversed from the previous example, right. And in fact, this is the order in which the disk usage command in Unix, if you ever have used this particular command in Unix, what it does is that if you type in this command in a directory, it tells you what is the total space occupied by the various subdirectories in there. So, the way it would list it out is, if you were to type the disk usage command in this subdirectory, it is first going to list out the total space occupied in this directory, then the total space occupied in this directory, and then eventually at the end it will list out the total space required here, because it would have computed this only after it had done this computation. And how does it do this computation? In a recursive manner. That is, to compute the total space required by this directory, it is first going to compute the total space required here, then the total space required here, and then add them up to get the total space required here. Yeah. So, that would be a post order traversal. Is this clear? Yeah.
So, which child will be visited first?
Okay. So, so your question is which child would be visited first? We are looking at ordered trees, right. So, that there is a notion of a first child, a second child, a third child, and a fourth child. So, the first child is visited first, the second next, and so on.
So, means the leftmost.
Yeah. So, if you have drawn the tree in such a manner such that the first child is at the left, is leftmost, then that's, we would say that the leftmost child is visited first, then after that the one to the right, and so on. So, it depends upon how you have drawn your trees, right. So, for binary trees, so what I had just shown you was traversals in general trees. So, it said pre-order, first visit the node, then visit the children nodes. In post order, first visit the children nodes and then visit the node. So, let us look at how this specializes to the case of binary trees, right. So, in a pre-order traversal, what are we saying? So, V is a node. If V is not null, if V is null, then there is nothing to be done. If V is not null, then in a pre-order traversal, we are first saying visit V. A visit is some generic computation, we do not know what it really is, right? It depends upon what your particular application is. So, we first say visit, then do a pre-order traversal on the left child and then do a pre-order traversal on the right child. So, note that this is a recursive procedure, right? We are calling pre-order within the procedure itself. How does this work? This will work by making the call to itself, right, when we are doing a pre-order traversal on the left child and on the right child. And the difference between pre-order and post-order here is that visit now comes at the very end. First you do a pre-order traversal on the left child, then you do a pre-order traversal on the, so you do a post-order traversal on the left child, then you do a post-order traversal on the right child, and then eventually you do visit V. Let's see if we have understood this. Let's look at an example. Right, this is my tree, it's a binary tree. I want you to tell me what the pre-order and the post-order traversal of this tree is. What we are doing when we visit a node is that we are just printing out the contents of the node, right. So, let us first look at pre-order. What do you think would be the first thing that would get printed if we are doing a pre-order traversal of this tree? This is the root. A, right. So, we come here, we print A. Then we have to go and do a pre-order traversal of the left subtree. So, when we do a pre-order traversal of the left subtree, we are going to come to the root of this left subtree and first print the node, first visit the node. Visit corresponds to printing the content. So, we will just print it out, right, B. Then we will go to the left subtree. Left subtree is C. So, we will come here, we will look at the root node, first visit the node. So, visit the node here means printing the content, so we will just print C. Then we try to go to its left subtree, but its left subtree is null, yeah, there is nothing there. So, then we go to its right subtree, which is also null, nothing to be done. So, now we are done with the pre-order traversal of this guy. So, where do we go now? To the right subtree, because first we went to visited the node, then we did a pre-order traversal of this left subtree, then we did a pre-order traversal. Now we have to do a pre-order traversal of this right subtree, which means that we first visit the node here, which is D, then we go left F, then again we try to go left null, go right null, nothing to be done, then we go to G, and now we are done with the pre-order traversal of this subtree. So, we are done with the pre-order traversal of the left subtree, we are done with the pre-order traversal of the right subtree, which means we are done with the pre-order traversal of this entire subtree. Yeah, we are done with the pre-order traversal of this subtree. So, now we would go to the right subtree. The right subtree has only E in it, so we would just print E and be done. This would be the pre-order traversal of this tree. Any questions here? Is it clear to everyone? Okay, let us do a post-order traversal now. Right? Which do you think is the first node that would get printed? C. Why is C the right answer? Let us see. So, we come to here to do a post-order traversal. So, this will be printed at the very end after I have done a post-order traversal of this and a post-order traversal of this. So, I will first try to do a post-order traversal of this. Now, when I try to do a post-order traversal to this, I come here. So, first I will do a post-order traversal of this, then I will do a post-order traversal of this and then print this node. So, I have to come and do a post-order traversal of this. For doing that, I will first do a post-order traversal of its left child, which is null, nothing to be done. I do a post-order traversal of its right child, null, nothing to be done. So, I am ready to now print the content of this node. So, the first thing that will get printed is C. Now, I am done with the post-order traversal here. So, now I come and do the post-order traversal of the right subtree. To do the post-order traversal of the right subtree, I once again come to the root here. I first do the post-order traversal of this left subtree, then of the post-order traversal of this right subtree, and then print this content. So, post-order traversal of this would, it is a single node, so it will just be F. Post-order traversal of this would be G, and then I would print the content of this, which means D. Ab iske baad what will we print now? So, we have done the post-order traversal of this, we have done the post-order traversal of this, so we can now print this node. So, we will print B. So, now we are done with the post-order traversal of this. Now, so we go to the right subtree, do the post-order traversal here, which means we will just print E, and then we are done with the post-order traversal here, we are done with the post-order traversal here. So, we can now print the root, which is A. So, this would be the post-order traversal. Is this clear to everyone? Yeah, how the procedure works. Okay, good. So, one use of post order traversal can also be in, so I am showing you another example for evaluating arithmetic expressions, right. So, this is an arithmetic expression, you can we want to evaluate this expression. So, how does one evaluate the expression? So, well, this is minus. So, in essence we have to compute what the value of this quantity is, what the value of this expression is, this sub expression is. Yeah, this corresponds to a sub expression. So, you have to compute what the value of this sub expression is, we have to compute what the value of this sub expression is, right, and whatever values we get we have to then take their difference, that will be the value of this entire thing. So, as you can see it is like a post order traversal now, we have to compute first the value of this, then the value of this, and then take their difference, which is the operator sitting in this node. And how do I compute the value of this? Well, I have to compute the value of this, I have to compute the value of this left subtree, I have to compute the value of this right subtree, and then do the division, because that is the operator sitting here. Yeah. So, we can write a procedure something like this. Suppose I say evaluate the expression corresponding to, let's say V is a node. So, V is, let's say, this root node here, I say evaluate this. So, if V is a leaf, then I just return the variable stored at V, because that is the value. The leaf just corresponds to numbers in this expression, right. Else if V is not a leaf, then that means that we are at some internal node. Yeah. So, to evaluate the expression corresponding to this node, I have to first evaluate the left. So, let us say evaluate V dot left child, this arrow should be the other direction. So, x, let us say x gets the value of that, y gets the value of the right child, right, when I evaluate on the right child, and if O is the operator, then I just compute x O y, whatever that operator O is, right, and return that value. That will be the value of the expression corresponding to node V. Yeah. So, this is pseudocode, of course, but I hope you understand what I am trying to say here. So, essentially it corresponds, so this is like a post order traversal, small modification. Question?
The problem in this would be how do we generate this tree given a mathematical expression?
Yeah, so we are not going to be addressing that problem. So, the problem of generating this tree given an arithmetic expression has to, you know, we will have to incorporate the priority rules to be able to generate such a tree. So, we will not worry about that for now, right. So, we are just looking at traversals. Given such a tree, how can you evaluate the expression corresponding to this tree? So, we have seen for a binary tree, we have seen a pre-order traversal and we have seen an in-order traversal, a pre-order traversal and a post-order traversal. There is a third kind of a traversal which is called an in-order traversal. So, recall that in a pre-order traversal, we visited the node first, then we went to the left, then we went to the right. In a post-order traversal, we first went to the left, then to the right, and then we visited the node. So, the third possibility is if we just visit the node between the visits to the left and the right. Right. So, there should be an AND between the visit to the left and the right subtree. So, the pseudocode for in-order traversal would look something like the following. So, if V is null, then we just get out, else we first do an in-order on the left child, then we visit the node, and then we do an in-order traversal on the right child. Right. So, these are the only three possibilities, these are three in a binary tree, right. So, whether you first go left, where do you visit the node? Either you visit it before you visit both the left and the right, or you visit it after you visit both the left and the right, or you visit it in between the visits to the left and the right. So, these are the three possibilities and these are the three traversals that are known. So, let us just look at an example and see that we have understood in-order traversal, right. So, which is the first node which will get printed? A? So, first to do an in-order traversal, we come here, we will first have to do an in-order traversal of this guy, of this left subtree, then we come here and then we do an in-order traversal of the right subtree. So, to do an in-order traversal of the left subtree, we will come here, we will first do an in-order traversal of the left, then the right, and then we will print the content of this. To do an in-order traversal of, sorry, first the left, then we will print the content and then go right. So, to do an in-order traversal of this, well, this is a single node, so it just corresponds to printing C out, right. So, that is the first thing we will print. Then we will be printing the content of this, which will be B, and then we will have to do an in-order traversal of this right subtree. Right subtree in-order traversal. So once again we will first print out F, then D, and then G, and now we are done with the entire in-order traversal of this left subtree. So we will now print out A, and eventually we will print out E. Right? So that would be the in-order traversal of this tree. So are these three traversals clear to everyone?
Yes.
So there is another way of traversing a tree, and that's called an Euler tour. Right? So suppose this is the tree corresponding to an arithmetic expression, and this tour says that okay, so the tour is basically the one drawn in blue here. Right? So we start from here, keep going down, when we hit a leaf we go up to its parent, then go to the right subtree, right, and so on and on. Okay? So it's a generic traversal of a binary tree, and all the three traversals that we've seen, pre, post and in-order traversal, can be viewed at as special cases of this Euler tour traversal. Right? So each node is basically getting visited thrice. Why? Because once we are coming like this, then other time we are going like this, touching this node, let's say, and the third time we are coming like this and touching this node. Right? So there are 3 times that we touch any node, except perhaps the leaf nodes, where you can say that perhaps you can count this as only once or twice or whatever you want to. But every internal node will be touched thrice in this manner. Yeah. So I should actually qualify every internal node of degree which has 2 children. If the node has only 1 child, then you will touch it only twice. Okay. So suppose this is the arithmetic expression, this is the tree corresponding to a certain arithmetic expression. I want to print this arithmetic expression out with parenthesis. Right? I want to draw the parenthesis, so I want to print it out in this manner. Okay. So I can do an Euler walk to print this thing. So so suppose I am here, before I start on the left subtree, I will print a left bracket. Then before I start on the left subtree, when I finish with the right subtree, I will print a right bracket. Right? This corresponds to taking this path up, going up like this. And when I am coming like this and touching this node, then I will just print out the content of the node. Understand what I am saying? So recall that every node was visited thrice. So when I am visiting it from the left, then I am essentially going to print a left bracket. When I am touching it from the right, I am going to essentially print a right bracket. And when I am touching it from below, I am going to print the content of this node. Yeah. So if you do that, then you will get exactly this. Yes. First I will touch this node from the left. So I will print first a left bracket, then I touch this node on the left, I will print another left bracket, I touch this node on the left, I print another left bracket, I touch this node on the left, I print another left bracket. So I get 4 left brackets to begin with. Then I come to this node. For a leaf, I will just print the content of the leaf and do nothing else. So I just print 3, then I am going to touch this node from below, so I am just going to print a star or a multiplication. Right? Then I come, I touch it from the left, so I print a left bracket, then I come here 1 and so on and on. Right? So you can think of this as essentially printing out this arithmetic expression as some kind of an Euler walk on this tree. So we can actually write a generic method for tree traversals and then specialize it for whatever particular application you have, whether you want to do a pre-order or a post-order or an order traversal or any such thing. Right. So so this is just a small example. So you want to do you want to traverse the node specified at this position. So if this is an external node, then you will, let's say, call this method called external. Right. We have not done anything here. We have just specified certain methods: left, external, is a method that you will invoke if the node that you are trying to traverse is an external node. Yeah, an external node is the same as a leaf node. So, if it is a leaf node, then that is the method you would invoke. When you visit the node, when you touch the node from the left, yeah, then you will invoke this method. Here you continue with the left child. When you touch the node from below, you will invoke this method. Then you continue with the right child, and then when you touch the node from the right, you will invoke this method. Right? And now you can specify what these methods are. Yeah. So, when you are, so by specifying these methods, you can create the traversal of choice. You can specialize this binary tree traversal, this generic tree traversal. Yeah. So, this is an abstract class. So, if you want to go into Java details, so this is an abstract class, which means that these methods in here particular init result is external. External of course is specified, but init result, external, left, below, right, these are left unspecified. Right? When in a class you leave certain methods unspecified, then it becomes an abstract class, because you cannot really create an object of that class anymore. But then you can at some point specify those methods, right, and in that manner, so create a subclass of this class which specifies these methods, and in that manner specializes this generic tree traversal procedure. This is a generic tree traversal procedure. So, if I were to specify left, below and right in a certain manner, then I could get a method, I could get a class for printing out arithmetic expressions, let us say. Yeah. So, let us see.
What was left result?
Left result was just trying to store. You want to know what left result was? This is just, so when I go from the left child, when I come back from the left child, maybe I compute a certain result, right. This could be used for instance when we in that example of disk usage, right, we wanted to compute what is the total space occupied by that directory, right. So, we computed the space required by, let us say, the left child, the directory in the left child corresponding to the left child, we compute the space required by the directory corresponding to the right child. So, those, when we computed that, those could be stored in r.left result and r.right result, and then we would compute their sum. That would be our final value. That would be the value we will return. Okay. So, let us just see how to specialize this for our printing arithmetic expression example. So, recall that if the node is a leaf node, then all we said was that we are going to print the content of that node. Yeah. So, that is what we are saying, just print out the element in that node. P is the position, just print out the element in that node, whatever is the element there. Okay. When we touch a node from the left, we said we just print out a left bracket. So, that is what we are saying, just print out a left. When we touch a node from below, we just said that whatever is the operator in there, we just print that out, and that is exactly what we are doing. And when we touch it from the right, we just print out a right bracket. So, once I have specialized these methods in this manner, now this becomes print traversal. So, this is the class which is extending binary tree traversal, and when I invoke the traversal method, it will now print out with the arithmetic expression, with the tree corresponding to an arithmetic expression, it will print out the arithmetic expression now in the parenthesized form, right. So, I could specialize the same class binary tree traversal to use it to compute the total space occupied by the files by a certain directory structure, right, by specializing these methods in a slightly different manner. So, let us continue with our discussion on pre and in order. So, suppose I give you the pre-order and in order traversal of a binary tree, right. I have mentioned this here. Can you use this to figure out what the tree is? Yes or no? Suppose this was the pre-order traversal and this was the in-order traversal of the binary tree. Both are given, yes. I give you these two. Can you use these to print out to tell me what the tree is? You can? Yes, sir. Why? Why can we do that? Let's see. So, given this pre-order traversal, what can I say first?
The nodes.
A is the root? Okay, if A is the root, so I have marked A the root. A is the root. Now, what should I do? B is left child?
Find A in the
In order.
Is this true that B is the left child? No, not necessarily. The tree might not have a left child at all. Yeah, or sorry, the root might not have a left child at all. That can happen. So, we cannot say anything. All we can say is A is the root.
We need to find A in order.
Now, let us find A in the in-order traversal.
E is right child.
So, A is the root, I know that. So, let me just put down a note for the root. And I know that I will search for A in the in-order traversal. Now, what do I know? I know that E is to the right. E is the right subtree. So, I know that this is the in-order traversal of the right subtree and this is the in-order traversal of the left subtree of A. Right? The green is the in-order traversal of the right subtree and the blue is the in-order traversal of the left subtree. Yeah. So, I am going to now once again, so I know that the left subtree has 5 elements in it. This is the information I know. So, in the pre-order traversal, the 5 elements following A would correspond to the pre-order traversal of the left subtree. Yes, and the one element following that would be the pre-order traversal of the right subtree. So, in essence, what have I managed to do? I have managed to identify what the left and the right subtrees are, and I know their pre-order and in-order traversals. I know the pre-order traversal of the left subtree and I know the pre-order traversal of the and the in-order traversal of the left subtree. So, my problem, I can use recursion now. So, I know E is the right subtree and now I can basically work on this problem where I am given the pre-order traversal of now another tree, the pre-order and in-order traversal of a tree, and I need to figure out what the tree is, and whatever is the tree is I will come and plug it as the left subtree of A. Yeah, clear to everyone? So, let us continue with the example and let us see what we will do now. So, once again we are going to B is the root of this left subtree, right, whatever argument we used before. So, B is the root of the left subtree, we are going to see where B is in here, B is here and B is the root. So, this would be the left subtree of B now, C, and FDG is going to be the right subtree of B. So, on the left I have only one element, so that would be C here. So, C, this would be the left subtree and this would be the pre-order traversal of the right subtree. Yeah. So, I figured out that C, so since on the left there is only one, so I can put that C down. I do not know what the right subtree is yet, I just know its pre-order traversal and in-order traversal. I know that it has 3 nodes, the right subtree has 3 nodes. So, the problem recursively reduces to this problem of given the pre-order and in-order traversal of this 3 node tree, I need to figure out what the tree is. So, once again I know now that the root is going to be D, yeah, I look for D here, it is there. So, I know that on the left I have F and on the right I have G. So, I know the root is D and I know that the left subtree would have F and the right would have G. So, also see that, so, and I get something like this. Is this clear to everyone? You can translate this into a piece of code. Yeah, it will require some thought because you have to write it in a recursive manner. This is your second assignment which I have put it up on the web today. Okay.
So these are given as arrays?
This would be some input you will take from this from the user. Yeah.
The pre-order and the in-order.
The pre-order and the in-order traversal. And you have to compute, and you have to compute not the tree, but you have to compute the post-order traversal, which is simple if you have computed the tree, because then you can just do a post-order traversal of this tree and give the result. Now, it might be possible that, you know, given any arbitrary sequences, it is not necessary that there is a binary tree corresponding to that, right. So, you will also have to flag out an error if the sequences that are given to you are such that they could not possibly be the pre and in order traversal of any binary tree. Yeah. So, this is pre and in order. So, nothing sacrosanct about pre and in. So, given post and in, also you should be able to compute the tree, right. Suppose I give you post order and in order, can you use that to compute the tree? So, recall what did we do? We tried to first figure out where the root was, right. In the pre order, the very first element is the root. In a post order, the last element is the root always. So, first once you know the root, then you will search for the root in your in order traversal, and wherever you find that root, that neatly divides the thing up into a left subtree and a right subtree. Yes. So, once you know the left subtree, what the number of nodes in the left subtree, you can figure out what the post order traversal of the left subtree is, right. If there were 5 nodes in the left subtree, then the first 5 nodes of your post order traversal would be the post order traversal of the left subtree. So, in this manner again you can recursively work. Yeah. So, you can recursively figure out what the left and the right subtrees are and then plug them up to the tree. So, given a post and in order traversal also you can do. Given, now what is the third question? Given pre and post, can you do it? No. So, given the pre and post order traversal of a binary tree, you cannot uniquely determine the tree. And the reason for that is there can be 2 trees which have the same pre and post order traversal. So, suppose I gave you this pre order traversal and this post order traversal, right, 3 node tree. Okay. So, what do you think is the tree? This is a tree with this pre order traversal, A, B, C. Post order traversal will be C, B, A. This tree also has the same pre and post order traversal. A, B, C is the pre order traversal, post order traversal is C, B, A. Right? Which of these trees is the right one? You do not know. Both of them, right? So, there is no unique tree.
C as the right child also.
We could also have had C as the right child. So, these are only 2, but there could be many trees that you could construct. Yeah. So, that is the problem. Given a pre and post order traversal, you cannot uniquely determine the tree because there could be many different trees with the same pre and post order traversals. Yeah. But here note that what was happening was that your tree, some nodes in the tree had only one child. Suppose I gave you this information that every internal node of the tree has 2 children.
Complete.
Not complete. Every internal node of the tree has 2 children. What is that called? This is an example of a tree in which every internal node has 2 children. This is also not, this is not a full tree. Well, this is just a tree with every internal node having 2 children, right? There is no name to it. Right? Suppose I gave you this information. Did you say Indian tree? Okay. Then what? So, if each internal node of the binary tree has at least 2, no sorry, has exactly 2 children, right, because the binary tree, so there should be exactly 2 children, then actually you can use the pre order and post order to determine the tree uniquely again. And let us see, just as an exercise, why this is true, right. So, I gave you the pre and post order traversal, right. Now, what can you say? What is the first thing you can say?
A is the root.
A is the root, yeah, yes, A is the root. So, we can quickly draw the root. Now, what can you say?
B is the left.
B has to be the left child.
D on the left, D on the right, E must be the right child.
That's because it has two children.
Pardon?
That's because it has two children. So
It has two children, yeah.
So it
So we
must be the
know
left
that there is something on the left, or actually I have done the example with on the right. Okay. So what can I say is the right child of A? A has a right child because every node has two children. What is the right child of A?
it has to be.
It has to be E. Right. So since my example I have worked it out with that, so E I know is the right child from here, from this picture, and now I see where E is here. Yeah. Now E is here, and after E there is nothing here. What does that say? E is a leaf. That says E is a leaf, right? Because in a pre-order traversal, I would have first visited E and then gone to its children, but there is nothing following it. So which means that there is nothing after E has no descendants, so to say. So basically this means that then the left subtree has B, C, D, F, G. So E is the right child, and the left subtree has B, C, D, F, G as the pre-order traversal, and C, F, G, D, B as its post-order traversal. And now the same thing, since I managed to divide, I am going to continue, right. So I have B, C, D, F, G as the left, as the pre-order traversal of the left subtree, and C, F, G, D, B as the post-order traversal of the left subtree. So once again, I know now that the root is B, I draw out the root, right. Now what do I know about the right child of B? It's D. I know the right child is D. I see where D is here, right. I know right child is D. I draw. So D is the right child. So everything that follows D has to be in the right subtree. Everything that follows D in the pre-order traversal has to be in the right subtree. Why? Because in the right subtree, when I did a pre-order traversal, I would have first visited D and only then would have visited the other elements. Yeah. So DFG, that means form the right subtree, and C forms the left subtree. So the left subtree has only one element, so that's what I am going to do here also. Right? This one element would be my left subtree, and this would be my right subtree. So now that I have figured out the left subtree, which has only a single element, I can just draw it. Yeah, and now I know DFG. I know that my right subtree is DFG. Has nodes DFG, where pre-order traversal is DFG and post-order is FGD. So now I know root is D. Actually, I have already drawn that out. I know the right child is G. G is here. There is nothing beyond. So that means that G has no children further. I can draw that out, and then I know what remains is the left subtree. There is only one node, so it is to the left. Yeah. So you can do the same thing. I am just showing it to you at a high level. In fact, this is the level I will be following for all the algorithms we do in this class, right. The code, you will have to translate it into code, right, what you have to do as recursion or whatever it is. So you will have to, so the idea of the assignments would be that many of these algorithms you should learn how to, or you should figure out how to best program them efficiently. Are there any questions till this point? Right. So you can write down the code also for this. You can, given the pre-order and the post-order traversal of a binary tree, every internal node of which has exactly two children, you can even use that to figure out what the tree is. Yeah. So why did we work with two traversals? Why can't we just take pre-order, and so given just a pre-order traversal, can I use that to figure out what the tree is? Given just a pre-order traversal, can I figure out what the tree is? So we had, let's say, this as the pre-order traversal here, right? A, B, C, D, F, G, E was a pre-order traversal of this tree. This is one tree with this as the pre-order traversal. Can you think of another tree which has this as the pre-order traversal?
Every child have a left child.
I could just have all of the nodes in one line, so to say, right? A, B, C, D below it, F after it, G after it, E at the very end, right? And I could get a huge number of different combinations, all of which would give rise to the same pre-order traversal. Yeah. So, so with just the knowledge of one traversal, you cannot really do much. Similarly for post order, similarly for in order. Right? Even if I were to give you the in order traversal of this, you can construct many different trees with the same in order traversal. So, just using one you cannot really do anything, but two suffices for most purposes. In the only case when 2 doesn't suffices, when you are given the pre-order and the post-order traversals, in which case it doesn't if the binary tree, some internal nodes of your binary tree could have only one child. But if you are told that every internal node has 2 children, then even that is sufficient. Right? More questions?
Can you find how many binary trees can we get given only in order, given only pre-order?
Can you count the number of binary trees given only let us say a pre-order traversal? What do you think?
Yes, sir. Yes, sir.
2 to the power n minus 1. Why?
2 to the power n minus 1.
Why?
Because at every point we can say it is on the left or it is on the right.
Yeah, it is at least 2 to the power n minus 1, right? Why? Because 2 to the power n minus 1 just came from so 2 to the power, so we said A, B, C, D, E, F, let us say is my is the pre-order traversal of a binary tree. Right. So, we said A, B, C, D, E and F. This is one, and all you are saying is, well, I can make each one of them either a left or a right child, right, of its parent. So, this could be one. The other option could be that I decide A, B, C, D, E, F and so on and on, right. So, just since each of the node can be either a left or a right child of its parent, but there are many other possibilities, right. Pardon?
This is the minimum number.
This is the minimum, the absolute minimum, right. You can have many other possibilities. Yeah. So, there could be lots and lots of things possible.
I think is there a fixed number? If I have given A, B, C, D, it will be a fixed number.
Yes.
6.
It will be fine.
Yeah, of course it will be finite because there are only a finitely many different trees with 6 nodes on them. So, it will be from some finite number and it will be just a function of n. Exactly. Yeah, but I do not know how to compute the closed form expression for such n. More questions? Okay. So, with that we will stop today's class. So, what we looked at was tree traversals, how to traverse. So, 3 different ways of traversing trees. In order, pre-order and post-order traversals for binary trees, and for general trees there is no notion of an in-order traversal, right, as you perhaps understand. Why is there no notion of an in-order traversal for general trees? Right. So, because if a node has 3 children, then when do you visit the node itself, right? After visiting the first child or after visiting the second child, or when? Right? So, but in a binary tree there is a notion of a left and a right. So, first you visit the left, then you visit the node, then you visit the right. So, there is also a notion of an in-order traversal, and we saw some applications of these and how given in order, pre-order, post-order 2 of these traversals, you can figure out what the tree was which gave rise to those traversals.